In Chapter 20, we investigate the relationship between microscopic and macroscopic properties of atoms. We will begin by discussing the origins of gas pressure and further describe what temperature actually measures. Let's get started. Some remaining issues include why the ideal gas applies so broadly, why the molar specific heat is roughly the same for all monatomic gases and elemental solids, and what is temperature actually a measure of? We can motivate answers to these outstanding questions by studying the microscopic behavior of the system's atoms and molecules. What is the cause of gas pressure? Gas pressure is the result of collisions of the constituent molecules with the walls of the container. We will be able to determine a root mean square speed for the gas molecules by relating the ideal gas law to a microscopic calculation of the gas pressure. We have said previously temperature is a measure of the average translational kinetic energy of atoms in the gas. When two systems interact thermally, they exchange energies through collisions until both systems have the same average translational kinetic energy per particle. When this process has achieved equilibrium, the systems reach a common final temperature. We will also explore the second law of thermodynamics. We can interpret this as a statement that energy transfer as heat is spontaneous from a warmer system to a cooler system. We will add the concept of entropy to our discussion as well. In so doing, we will see that the evolution of systems can be understood because some macroscopic states are vastly more likely to occur than others. With our goals laid out for us, we next move to discuss these topics in greater depth. A gas consists of a vast number of molecules, each moving randomly and undergoing millions of collisions every second. Shown is the distribution of molecular speeds in a sample of nitrogen gas at 20 degrees Celsius. The micro-macro connection is built on this idea that the macroscopic properties of a system, such as temperature or pressure, are related to the average behavior of the atoms and molecules. A single molecule follows a zigzag path through a gas as it collides with other molecules. The average distance between the collisions is called the mean free path. It is inversely proportional to the number density of the gas molecules and is also inversely proportional to the square of the radius of the molecules. Let's try one of the quick check questions. The temperature of a rigid container of oxygen gas, O2, is lowered from 300 degrees Celsius to 0 degrees Celsius. As a result, the mean free path of oxygen molecules, A, increases, B, is unchanged, or C, decreases. Since the mean free path depends upon the particle density and the radius of the molecules, but not on temperature, the mean free path is unchanged. Let's look at the first example from your textbook's chapter. What is the mean free path of a nitrogen molecule at 1.0 atmospheres of pressure and a temperature of 20 degrees Celsius? The radius of the diatomic molecule is roughly 1 angstrom. If we solve the ideal gas law for the particle density, we have that N over V equals P over kBT. Plugging in values, we have that the density of molecules is approximately 2.5 times 10 to the 25 per cubic meter. The mean free path is then roughly 230 nanometers. Why does a gas have pressure? We have suggested that the pressure is due to collisions of the molecules with the walls of its container. The steady rain of a vast number of molecules striking a wall each second exerts a measurable macroscopic force. The gas pressure is the force per unit area resulting from these molecular collisions. The figure on this slide shows a molecule that collides with the container wall, exerting an impulse on the wall. We arrange our axes such that the x-axis is normal to the wall. We examine specifically the change in the x component of a representative molecule's momentum. Assuming purely elastic collisions, the change in the x component of a representative molecule's momentum is minus 2 mvx. If we count a number, n subcollisions, of these events over a small time interval, delta t, then the total change in the x component of the momentum of the gas is minus 2 times n subcollisions times m times v sub x. Recall that F equals delta P divided by delta T. Then the force on the gas is minus 2 times n subcollisions times m times v sub x divided by delta T. By Newton's third law, the force that the gas exerts on the wall is then 2 times n subcollisions times m times v sub x divided by delta t. If we consider that a particle traveling with a speed vx can travel a distance vx delta t in time interval delta t, assuming random motion, we assume that half will be moving towards the wall and half away. We can then define a volume of area A times Vx delta T containing twice as many molecules as will strike the wall in time interval delta T. The number of collisions in time interval delta T is half times the molecular density times the area A times Vx delta T. The pressure is the force on the wall divided by the area. Again, the random motion implies that 1/3 VRMS squared equals Vx average squared equals Vy average squared equals Vz average squared. We wind up with the pressure is 1/3 the molecular density times m times VRMS squared. VRMS is equal to the square root of the mean of the speed squared. Let's try another quick check question. A rigid container holds both hydrogen gas, H2, and nitrogen gas, N2, at 100 degrees Celsius. Which statement describes their RMS speeds? A. VRMS of H2 less than VRMS of N2. B. VRMS of H2 equals VRMS of N2. Or C. VRMS of H2 is greater than VRMS of N2. Since the mass of a hydrogen molecule is less than that of a nitrogen molecule, the RMS speed of the hydrogen gas is greater than that for nitrogen gas at the same temperature. The thing we call temperature measures the average translational kinetic energy, Ke average, of molecules in a gas. A higher temperature corresponds to a larger value of Ke average, and thus to a higher molecular speed. Absolute zero is the temperature at which Ke average equals zero, and all molecular motion ceases. By definition, Ke average equals half mVRMS squared, where VRMS is the root mean squared molecular speed, using the ideal gas law. We previously found Ke average equals 3/2 kBt. By equating these expressions for kinetic energy, we find that the RMS speed of molecules in a gas is equal to the square root of 3 kBt over m. A rigid container holds both hydrogen gas, H2, and nitrogen gas, N2, at 100 degrees Celsius. Which statement describes the average translational kinetic energies of the molecules? A. Ke average of H2 less than Ke average of N2. B. Ke average of H2 equals Ke average of N2. Or C. Ke average of H2 greater than Ke average of N2. Since temperature is a measure of the average translational kinetic energy of the molecules in the gas, if the two gases are at the same temperature, then the average kinetic energies of the molecules are the same. Here we see the relationship between the macroscopic measurables of pressure and temperature to the microscopic quantities of molecular density and average translational kinetic energy per molecule. Pressure equals 2/3 times the molecular density times the average translational kinetic energy per particle. Temperature equals 2/3 times the average translational kinetic energy per particle divided by Boltzmann's constant. The total microscopic kinetic energy, Ke total, equals N times Ke average. The thermal energy of the system is the microscopic kinetic energy plus the microscopic potential energy. E thermal equals 3/2 times the number of molecules N times Boltzmann's constant Kb times the absolute temperature T, which also equals 3/2 times the number of moles N times the ideal gas constant R times the absolute temperature T. The change in internal energy is 3/2 times the number of moles times the ideal gas constant times the change in temperature. The change in internal energy for any ideal gas process equals the number of moles times the molar specific heat at constant volume times the change in temperature. Comparing these two equations, we find that for an ideal monatomic gas, the molar specific heat at constant volume is 3/2 times the ideal gas constant. We remind ourselves of and formalize the equipartition theorem. Atoms in a monatomic gas carry energy exclusively as translational kinetic energy, 3 degrees of freedom. Molecules in a gas may have additional modes of energy storage, for example, the kinetic and potential energy associated with vibration or rotational kinetic energy. We define the number of degrees of freedom as the number of distinct and independent modes of energy storage. The equipartition theorem states that the thermal energy of a system of particles is equally divided among all the possible degrees of freedom. For a system of n particles at temperature T, the energy stored in each mode or degree of freedom is half n kBT or half nRT. The figure reminds you of the bed spring model of a solid with particle-like atoms connected by spring-like molecular bonds. There are 3 degrees of freedom associated with kinetic energy, plus 3 more associated with the potential energy in the molecular bonds, equaling 6 degrees of freedom total. We recall that the energy stored in each degree of freedom is half NKBT, so the thermal energy of a solid is 3 NKBT, or 3 nRT. For diatomic molecules, in addition to the 3 degrees of freedom from translational kinetic energy, a diatomic gas at commonly used temperatures has 2 additional degrees of freedom from end-over-end rotations. This yields 5 total degrees of freedom, so that the internal energy is 5 halves N kBT, or 5 halves nRT. The molar specific heat at constant volume is 5 halves R. Here we have a table detailing the number of degrees of freedom, the internal energy, and the molar specific heat of monatomic gases, diatomic gases, and elemental solids. Experiment tends to bear out these expectations. Systems A and B are both monatomic gases. At this instant, Ta is greater than Tb, Ta equals Tb, Ta is less than Tb, or there's not enough information to compare their temperatures. Since we have established that E internal goes as 3 halves N kBT, the temperature T is proportional to E over N. The temperature in A is greater than the temperature in B. Consider 2 gases, initially at different temperatures, with T1I greater than T2I. They can interact thermally through a very thin barrier. The membrane is so thin that atoms can collide at the boundary as if the membrane were not there. Yet atoms cannot move from one side to the other. The situation is analogous on an atomic scale to basketballs colliding through a shower curtain. The figure shows a fast atom and a slow atom approaching the barrier from opposite sides. During the collision, there is an energy transfer from the faster atom side to the slower atom side. Heat is the energy transferred via collisions between the more energetic or warmer atoms on one side and the less energetic or cooler atoms on the other side. The two sides reach equilibrium when the atoms on each side have on average equal energies. The average translational kinetic energy on the two sides must balance. Because the average energies are directly proportional to the final temperatures, the temperatures in the two populations are equal. The final thermal energies of the two systems after reaching equilibrium are E1 final equals quantity, the number of moles in system 1, divided by the total number of moles in systems 1 and 2, end quantity, times E total. And E2 final equals quantity, the number of moles in system 2, divided by the total number of moles in systems 1 and 2, end quantity, times the total energy. We have done no work because the membrane stays fixed. The heat into each gas is then equal to the change in its internal energy. By conservation of energy, the heat into one must equal the heat out of the other. Let's look at an example in this vein. A sealed, insulated container has 2 grams of helium at an initial temperature of 300 Kelvin on one side of a membrane and 10 grams of argon at an initial temperature of 600 Kelvin on the other side. How much heat energy is transferred and in which direction? What is the final temperature? We use the molar mass to find that there are 0.50 moles of helium. Similarly, we find that we have 0.25 moles of argon. The initial internal energies are 1,870 joules for helium and 1,870 joules for argon. Even though the two systems have equal thermal energies, they are not in thermal equilibrium, as is demonstrated by the difference in temperature. The total energy is 3,740 joules. We then apply the equations to divide the total energy between the two systems. The helium winds up with 2,493 joules, and the argon winds up with 1,247 joules. The heat energy entering the helium is 623 joules, and the heat energy leaving the argon is 623 joules. The helium's temperature rises by 100 Kelvin, and the argon's temperature decreases by 200 Kelvin. The equilibrium temperature is then 400 Kelvin. When two gases are brought into thermal contact, heat energy is transferred from the warm gas to the cold gas until they reach a common final temperature. Energy could still be conserved if heat was transferred in the opposite direction, but this never happens without intervention. The transfer of heat energy from hot to cold is an example of an irreversible process, a process that can happen only in one direction. Molecular collisions are reversible in that the paths make sense, forwards or backwards. However, car crashes are not reversible. The figure shows two boxes containing identical balls. Once every second, one ball is chosen at random and moved to the other box. What do you expect to see if you return several hours later? Although each transfer is reversible, it is more likely that the system will evolve towards a state in which N1 is approximately equal to N2, then toward a state in which N1 is much greater than N2. The macroscopic drift towards equilibrium is irreversible. Scientists and engineers use a state variable called entropy to measure the probability that a macroscopic state will occur spontaneously. It is often said that entropy measures the amount of disorder in a system. In principle, any number of heads are possible if you throw n coins in the air and let them fall. If you throw 4 coins, the odds are uh, 1 in 2 raised to the fourth power, or 1 in 16, of getting 4 heads. This would represent a fairly low entropy state. With 10 coins, the probability that n heads equals 10 is half raised to the 10th power, which is roughly 1 over 1000, which, which corresponds to a still much lower entropy. With 100 coins, the probability that n heads is 100 has dropped to roughly 10 raised to minus 30, and it is safe to say it will never happen. Entropy is highest when n heads is roughly n tails. Macroscopic systems evolve irreversibly towards equilibrium in accordance with the following law. The formal statement of the second law of thermodynamics states that the entropy of an isolated system or group of systems never decreases. The entropy either increases until the system reaches equilibrium, or if the system began in equilibrium, stays the same. This law tells us what a system does spontaneously, on its own, without outside intervention. Order turns into disorder and randomness. Information is lost rather than gained. The system runs down. The second law of thermodynamics is often stated in several equivalent but more informal versions. Our first informal statement is when two systems at different temperatures interact, heat energy is transferred spontaneously from the hotter to the colder system, never from the colder to the hotter. The second informal version is the time direction in which the entropy of an isolated macroscopic system increases is the future. Establishing the arrow of time is one of the most profound implications of the second law of thermodynamics. Okay, that's all for chapter 20. As always, you are all awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your days, but not so much that we don't see you next time.